This is Math 139, Section 3.11. We're now going to look at another kind of logarithm and exponential function called the natural log and exponential. In order to explain what that means, I need to start by talking about a special kind of number. In math, we have a few numbers that have special uses, and we often give them special symbols to make them easy to refer to. One example that you all know about is pi. Right? Pi is the number approximately 3.14159 and so on. We know its decimal form goes on forever without repeating or terminating. Why do we decide to assign a name to that particular number? Well, basically because it's useful, right? It does things for us in math. For example, we could find the area of a circle by taking pi times the radius squared. Or we could find the circumference of a circle by taking 2 pi times the radius. So the reason that we define this number is because it's useful to us. It helps us out with mathematical calculations. There's another number in math that's special because it's useful, and that's represented by the symbol e. You may or may not have met e before. E is approximately 2.718, but again, just like pi, the decimal form goes on forever. E is referred to as Euler's number. Named after a very famous mathematician, Euler. I know it looks like Euler, but it's pronounced Euler. And E stands for the E in Euler's name. Why is E so useful? Why do we want to define a number special for this particular symbol? Well, it turns out it's also very useful in certain applications, kind of like pi was useful to us. And we're going to talk more about that in just a little bit. I'd like to start with a few mechanics. We're going to talk a little bit more about using e with log and exponential functions. And then in part B of this video, we'll talk about exactly what types of applications use the number e. So, we define the natural exponential function as the exponential function with a base of e to the x. We define the natural logarithm function as the inverse of e to the x, the log base e of x. And that actually looks really weird to me because we actually never really write it as the log base e. We write it as ln of x, where the ln stands for natural logarithm. It is an L, not a capital I. I know they look the same in print, so be careful when you type into MyMathLab. ln of x. So e to the x and ln of x, or natural log of x, are inverse functions. They do and undo each other, just like any other log and exponential function with the same base. Keeping that in mind, if I asked you what is the natural log of e to the fifth, you would simply say, well, natural log and e are inverses. Therefore, that equals 5. Or if I wanted to know what is e raised to the power of ln x, again, the e and the ln are acting directly on one another, and they are inverse functions. And so once again, all I have left here is x. E and ln are inverse functions. They act exactly like any other inverse functions that you've seen before. Because of that, we can use e and ln in equation solving. If I wanted to solve for x in this first equation, I'll notice it's an exponential equation. And my exponential is actually the e to the 3x minus 1. I'll need to get that by itself. I'll need to isolate that first. So we'll subtract the 5. And divide by the 8. Let's see, what is that? 28 divided by 8. I think that actually comes out reasonably nicely as a decimal. Yes, 3.5. All right, to get to the x, I need to get rid of the exponential, the base e. And in order to do that, I'm going to use the natural log because it is the inverse of the exponential base e. Of course, whatever I do on one side, I must also do on the other. So I'll also do a natural log on the right-hand side. So I can allow my ln and my e, my inverse functions, to get rid of each other. And I have 3x minus 1 is approximately the natural log of 3.5, about 1.25276. Guess I'm getting a decimal approximation this time. Our instructions didn't say whether we wanted exact or approximate, so I'll do approximate this time. We'll add 1. 3x is 2.25276. And I'll follow that right along in the calculator, add 1 to that, and then we can divide by the 3 to be about 0.751 for a final answer. All right, let's try a couple more with logs and exponentials. In this next function, or next equation rather, notice that I actually have e to the x in two different places in my equation. If I'm going to isolate the exponential, I need to start by getting those exponentials on the same side. So I'm going to subtract e to the x from both sides. Remember, that's really a 1 e to the x. So I have 2 e to the x minus 12 equals 44. I now need to isolate my exponential, which is e to the x. So we'll add the 12. 44 plus 12 gives me 56. And then divide by the 2. So e to the x is equal to 28. I need to get rid of the base e. The inverse of exponential base e is natural logarithm. So I'll take the natural logarithm on both sides. My inverses get rid of each other. And my exact answer would be the natural log of 28. My approximate answer is about 3.332. All right, this next equation has a natural log in it to start with. And again, we always want to start by isolating, so I want to isolate the natural log of 5x. We'll add the 3. Making that equal to 4, and then divide by the 2. So the natural log of 5x equals 2. Now I need to get rid of that natural log, so I'll apply the inverse function, which is the exponential base e. And that means I also need an exponential base e on the right-hand side. All I have left on the left-hand side is 5x. That equals e squared. So as an exact answer, x would be e squared divided by 5. I can get a decimal approximation for that. Let's see, second e to the x, e squared, divided by 5 is about 1.478. So there's exact and approximate. All right, one more equation. Notice I've got the natural log in two places here. So I need to combine my logs using the same log properties we just recently learned about in a previous section. In order to combine these logs, my first step is going to be to take this 2 and bring it up as an exponent. So I would have the natural log now of x to the 6th minus the natural log of 8x to the 5th equals 1. I can combine this difference as the log of a quotient. So the natural log of x to the 6th divided by 8x to the 5th equals 1. And then I'm going to simplify inside my parentheses. Subtracting exponents gives me x to the 1st on top, and that 8 is still on the bottom. All right, all that was just to simplify and get it down to one logarithm. Now I'm ready to get rid of the logarithm. I do that with the inverse function. The inverse of the natural logarithm would be the exponential base e. And I have to do that on both sides. There's my inverse functions. Get rid of each other. I have x divided by 8 equals e to the 1st, or just e. And for an exact answer, I have x equals 8e. That would be approximately, there's just a plain old e right above your divide sign, by the way, about 21.746. All right, so all of the rules or techniques that you've practiced for solving exponential and log equations with other logs and exponentials still apply to natural logs and natural exponentials.